Welcome to the IEEE panel on electric vehicle charging data in the clean energy transition. This panel is organized by the IEEE Digital Privacy Initiative and the IEEE Transportation Electrification Community. I'm Linda Zeger, and I will be moderating today's panel. I work at the intersection of the smart grid and data use in network communications, artificial intelligence, and additional modeling and analytics. We are pleased to have our three panelists joining us. Scott Dimitrowski, co-founder and CEO of Rolling Energy Resources, Anthony James, senior engineer and data scientist at Southern California Edison, and Mario Harper, computer science faculty at Utah State University. Electric vehicles have the potential to reduce greenhouse gases, thereby slowing climate change. They also have the potential to reduce additional pollutants and to enable a reliable electric grid. However, it is challenging to achieve these goals since EV charging, most of which for personal vehicles currently occurs in the home, requires power greater than other typical household appliances. The expected large increase in the number of EVs could strain the power grid, which was not designed for their larger loads. In addition to the need to overcome potential grid infrastructure limitations to accommodate all these EVs, in order to reduce emissions, it is necessary that the electricity powering the EVs comes from clean energy sources, such as wind and solar. However, these clean energy sources are intermittent and hence are not necessarily available when EVs may charge. Thus, techniques such as managed charging are needed to incentivize or control EVs to charge at opportune times so as to be able to utilize the clean energy resources like solar and wind. In order to do this, they need data, such as EV charging data, to provide the knowledge and situational awareness for things like managed charging. Data is used both for real-time operations and for long-range planning of the electric grid. It's used in artificial intelligence, as well as in physical modeling and simulations, and also to measure effectiveness of grid components and systems. Today, we're focused on the EV charging data. Today's panel is the first of several parts. In subsequent panels, we'll look more at privacy questions. But in today's panel, the focus will build a foundation for those subsequent discussions of privacy by today focusing on what data is collected, how it's used, and how it will benefit the public. If you have any questions during the session, please enter them, type them into the Q&A, and we'll try to address them later. We'll now turn to the three panelists and have them introduce themselves, as well as tell what data they collect, where it originates, what's the source of the data, and finally, why is this data important to collect and how it benefits the public. And we'll start with Scott.
All right, great. Thanks, Lynn. I'm going to go ahead and share my slides. Let me know if they're showing okay. Is that showing okay? All right, excellent, great. Yeah, I'm Scott Dimitrowski. As Linda had noted, I'm CEO, one of the co-founders of Rolling Energy Resources. And I'm going to reiterate a couple points that Linda made. And the first one is that EVs are expected to grow exponentially in terms of grid impacts, from about 1 million vehicles in 2020 to over 20 million vehicles in the next decade. So, this has been coined as the opportunity of the century for electric utilities, but it also comes with a risk, because when a single EV is plugged in and charging, it has the draw of multiple air conditioners at the same time. So, as Linda, had noted, if the load is not managed, there's a risk of blown transformers, power outages, and price spikes. So utilities need a way to get data off the cars and use that to manage the load. In terms of some of the benefits by doing this, utilities can avoid costly infrastructure upgrades. They can maximize renewables. Again, as Linda had noted, it is possible if you can manage charging to make it coincidence, with peak or excess renewables. And then also customer satisfaction. There are ways to use this data to, help educate customers and make them happier with their EVs. So in terms of sources of EV charging data, what's available right now, I tend to break it down into 4 categories. And the first one is EV telematics data. That's what, RER really focuses on, and that's talking directly to the car. Most EVs today are actually connected vehicles, 4G, 5G, Wi-Fi if it's available. And so there are ways to connect directly into the EV, the API. So it's similar to what you think of if you have an app and you're able to talk to your car, a customer would actually opt in and allow us access to that information. And the second way to get EV charging data is through plug-in device telematics. And so these are connected devices that go into the onboard diagnostic port for cars. And then again, there are ways to talk to those devices. They gather information from the car, and that can be used again to manage charging in different ways. And the most common way to to get charging data has actually been off of the EVSEs themselves. That's through connected chargers. There's a number of companies out there that make these. They're referred to sometimes as smart chargers. I'm going to show on the next slide. They're not totally smart all the time. But again, there are ways to communicate with the chargers, gather data and then manage charge. And lastly, there's AMI disaggregation. This is a method I'm seeing more and more now, which is actually trying to take customer bills and to disaggregate those into end uses, one of which, of course, would be EV charging, and then use that again to communicate with customers and help manage load through behavioral approaches. So in terms of comparing, each of these options in terms of charging data, we believe that telematics is the lowest cost, most scalable. You get home and away charge. You get the state of charge as well. As we're looking into active managed charging programs and thinking about stopping and starting charge, we believe it's important to get that. That is not available through connected chargers or AMI disaggregation. And then again, you could see telematics has access to a full range of OEMs and that ability to stop and start the car. So there's pros and cons with each of these. Ultimately, what I've heard, if we're trying to understand EV charging from the car, let's talk directly to the car. So that's what we do in terms of telematics. It's quick and it's easy. Usually an invitation goes out, the customer clicks a link, enters in email, first name, actually enters in the information from their OEM login. It auto-populate that. And then you can see the information that we get here: EV battery level, charging status, charging location, and that ability to stop, start, charge. And the uses for the data, which we're going to talk more about today on the webinar, but to highlight four. One is for grid planning, thinking ahead to when there's millions of EVs on the grid and how they're going to be managed. Customer education. And then I break load control into behavioral load control and active load control. And again, we could talk more about these during the webinar today. All right, thanks, Linda.
Thanks for the really great introduction, Scott. Now we'll turn to Mario.
Hello, everyone. I'm Mario Harper. I am at Utah State University, and I am the data thrust lead for the Aspire ERC. This is a National Science Foundation project and an engineering research center made by the NSF to go for clean energy, clean transportation, electrified transportation. Part of what we do as this large center, and we encompass many universities, both here in the United States and outside the United States. But we also work with many pilot projects across the country for new inductive charging roadways. So these are wirelessly charging roadways that as you drive over them, they will charge your vehicle. But we also work on projects with governments and DOTs. So I think we are currently we work at 11 state DOTs. And we also work with some of our larger partners, looking at electrified freight, looking at electrified buses, looking at mid-scale truck vehicles. And we encompass this intersection between what we need to do from a technical perspective. We need to make better chargers, faster chargers. We need to make better inductive systems inside the roadways. We need to make sure that all of these technical things happen. But we also care about the equity impact. We care about making sure that when we place a charger, is this charger going to be used by everyone who needs it now, or is this going to enable new adoption in areas and communities that haven't had access to this? Do we account for the fact that there are health concerns when we run these large freight vehicles in certain parts of a city? And we want to see what electrification might do for this. How much will it cost? What was the infrastructure? What do we need? Will the grid be able to support this thing? Just like was mentioned earlier by both of my compatriots, when you charge large vehicles, it takes a lot of electricity, and more so for buses and for semi trucks. They take an incredible amount of electricity to fast charge these systems. We'll talk about that later in this conversation. But we want to make sure that the data we collect gives us the information we need to make right policy decisions. We want to make sure state DOTs, state governments, and federal agencies understand what the impact of some of these things are. They are expensive. This infrastructure is not cheap. Putting in new EVSEs, especially at fast charge levels, means that we need to have grid buy-in. We need to talk to the power sources itself. So we have partners who are actually at the grid and at the generator level. And we understand what it is they need from large-scale electrification. We pull this all together through the data we collect. We cannot make a difference in the communities we want to impact without this information. And so what do we collect? Well, it's actually just like Scott said earlier, we collect information on state of charge. We collect information on how the vehicles are used, what the power consumption curves look like, what the battery degradation curves look like. We look at how much impact something will have if we charge it slowly, if we charge it very quickly, what times we charge it. Will the electric surface rail impact things? Will the price response impact things? Well, how do we incentivize behaviors so that we mitigate grid impact and we make sure we have a nice, equitable, and usable electrified transportation future? I'll leave it at that, Linda, and give it back to you.
Thanks very much, Marian, for pointing out the different range of EV charging, including heavy vehicles, including wireless charging. So it really is a huge range. Now we'd like to have Anthony introduce himself as well.
Everyone, welcome. My name is Anthony James. I'm a senior engineer with Southern California Edison in the Grid Innovation Group of the Asset Strategy and Planning Organization, which primarily supports transmission distribution. We serve over 15 million customers, over a 50,000 mile region. We plan to support the electrification of 75% of our vehicles in the state, in our region by 2045. And just to let you know the significance or the level or the transformative change that we're dealing with when we think about an average home load, we're looking at about 1 kilowatt on average in terms of peak. With electric vehicles, we're looking at some of the old chargers from 1.44 kW to as much as 17 or 19.2 kW. So we're likely to see a significant increase in load on the system that the system was initially designed for. So I'm responsible among many of the other engineers who are advancing new and cutting-edge technologies in the research, development, and demonstration area to enable SCE's strategic capabilities, either partnering internally or externally with national labs, utility research institutions like EPRI, and technology companies, for example, like GE is one example, or startups to EPRI. I was also recently the lead on the EV load study work, which involved up to 12 different work streams, which we conducted to inform our T&D electric vehicle integration strategy. And I'm also the distribution grid analytics lab lead, where we focus on enabling new capabilities to support DER integration to either mitigate impacts or realize new value from DERs like electric vehicles, all in either the market planning or operational areas. So from our perspective, in terms of where the data originates, a little bit different than Scott. We generally, there are three areas. Two, we're currently receiving data from. One, we're sort of looking at in the future. One is related to meters. So we have dedicated meters to EVs, residential, commercial, not so much the residential side. Most of the meters combine EV loads with other loads. And so with those meters, we collect consumption information. Then we also collect customer information, usually through our rebate programs, identifying who the customers are, the types of vehicles, and some other information that's useful to us. The third area is where looking at in the future where we plan to integrate what Scott had talked about in terms of vehicle telematics into our DERM systems, which the DERM stands for Distribution Energy Resource Management System. And so this is part of our overall energy management system for the distribution area, where we integrate and leverage DERs to better manage issues or integrate these DERs like EVs to realize value for the system for our customers. So when we think about why it's important to collect this data, EV charging, primarily, as I mentioned before, our Pathway 2045 transportation electrification strategy requires us to support the electrification of 75% of our electric vehicles. So we're talking about residential light-duty vehicles, commercial light-duty fleet, medium-duty and heavy-duty vehicles. And primarily today, through our e-mobility programs, we incentivize electric vehicles through rebates and incentives. So we use information from those programs to help with better planning for the future to enable we have the right amount of capacity for our system to integrate electric vehicles. And like I mentioned before, which we can go into more detail, to inform the EV integration strategy in terms of standards, how we can better monitor the system, and play well with these resources, enable customers to be prosumers with electric vehicles.
Thanks very much, Anthony, for that wide array of work in this area. We'd now like to turn to delve a little further into the knowledge gained from the data, how it's used, what are the benefits for public use. We've heard things about infrastructure planning, because that can be very costly. We've heard about health benefits and making sure users who weren't necessarily represented in the initial data do have access to chargers, and we've heard a lot of other things as well. So it'd be great if each of you could expand on those benefits and uses of the data, and we'll start with Anthony.
Sure. So when we talk about the benefits, primarily we're talking about ensuring reliability and affordability for customers, customer satisfaction, ensure we have the capacity available for customers to charge electric vehicles basically when they need to, and to ensure and minimize risk, ensure that we manage overloading, we don't have to deal with equipment failures. And these are kind of the primary benefit areas, and to go into some more detail in terms of realizing these benefits, generally I would say would start with the grid studies that we would need to do to develop and validate strategies for EV integration, like for example, managed charging. We just did a study with Pacific Northwest National Lab. I believe the report will be available online, where we looked at simulating EV adoption every 5 years into the future and looking at what our grid needs are and potentially allocating EV adoption transformers using algorithms that we developed, evaluate managed charging, the benefits of managed charging. Distribution standards, how we need to rethink our distribution standards to integrate electric vehicles, both on the commercial side and the residential side, which requires different strategies. In looking at customer EV charging patterns, they're quite different. We looked at 12 different residential segments, and there's a multitude of different commercial segments that we look at to kind of inform our infrastructure strategy as well as our T&D integration strategy. Adapting to new EV integration is harder on the commercial side because it's harder to predict medium and heavy duty adoption. Although, again, back to the benefits, we also look at the importance of power quality, ensuring that we're able to maintain the right level of voltage and we don't overload the system, which can cause wear down and public safety issues. In more detail, and this maybe for if there are any utilities on the call, we look at load factor at the transformer. We develop methods to forecast an 8760 profile view of what that load factor capacity utilization is on the transformer to inform and plan ahead for standards. We look at the potential coincidence of EV loading and system loading at the transformer to better inform our standards. Initially we had some challenges identifying EVs we developed a method to identify significant more EVs so we could do better representative studies or identify optimal public charger EV locations for customers. So they have charging locations when they need it. As I mentioned before, the EV load and the other loads are combined at the meter, which makes it very hard to assess the behavior. So we had to develop a method to disaggregate the EV load so we could better characterize and forecast the load, again, to inform our standards, but also at the system level, because we have to do, multi-level system planning for the entire grid for transmission distribution capacity. Other benefits as it relates to this work includes also being able to do more real-time monitoring, especially at the transformer related to conductors or cables connected to the transformers to ensure that those cables or conductors also don't become overloaded. It's very hard to determine when EV is going to charge, and the coincidence of charging can vary. So it really requires us to do more active monitoring because on average, we can plan for the grid, but it's planning for the exceptions that's a little bit difficult. So we have to do more monitoring. And then, in a kind of a larger view, we have to be able to integrate the non-wires managed charging aspects into any integration, looking at traditional upgrades versus active managed charging, behavioral load shifting, along with other emerging technologies to continue to manage voltage and thermal violations. And then the last thing in terms of benefits to customers, evaluate whether the rates that we're designing are working. If they're supporting the needs of the customers, if they're also supporting the needs of how we can optimally manage our grid for customers.
Thanks very much, Anthony. You mentioned a number of areas and benefits. And I think one of them that Scott also had mentioned is managed charging. So it'd be good to hear from Scott now on the benefits of managed charging or any additional benefits and knowledge derived from the data.
Okay, sure. Thanks. Yeah, and I'm going to share my screen again. It's okay. It's a little bit easier to show some slides as I'm talking here. Yeah, just, I mean, as Anthony, had noted, the grid planning is really key. I do highlight, a number of items here, the typical metrics that I think are helpful to look at, in some ways that, even a higher level than Anthony had mentioned, but, is charging usually done at home versus away? How is that going to change over time as utilities build out the charging, infrastructure? Because right now, 80 to 90% of charging is done at home, at least on the residential side. How many homes have level 1 versus level 2 chargers? Battery remaining, typical, load shapes. So those sorts of questions are really key right now in these early days of EV adoption. This is something Anthony had also mentioned about predictive analytics, because as we monitor data over time with the cars, we're going to understand typical charge patterns and, when they're going to charge. So we could look, like you could predict a future where, it's 4 p.m. And if we're monitoring the state of charge on the cars, you can predict, what the load is likely to be at 5 p.m. You could even predict where that charge is going to happen. And again, by mapping to the cars, to the, the transformer or the feeder, you can even have, the exact, location where there might be stress on the grid and, be proactive to manage that. I do want to add one other thing, Linda, as well, which we haven't talked much about, is how to use the data for customer, education. And these are my actual bills. I like to show these. I also joke the only thing I got from my utility, at the time when my bills double, was a home energy report that I was now using more energy than my neighbors, and I should try to run my dishwasher with full loads. So it was not very helpful. So I do think, there is a real risk if we don't take the data off of EVs and, the cost to charge and try to, do something with that to educate customers about how they actually are saving money versus having to fill up a gas tank, because there is a risk of sticker shock, especially when you pay by the month and not by the tank. In one study we did, this is Massachusetts, on average, there was about a 50% increase in the customer bill. So, I wanted to note that. I'm going to skip this in terms of managed charging. You asked about that. There's really two approaches that we see right now. One is behavioral load control, and that's using the data again to feed back to the customer, show them their charging patterns, and give them, nudges through behavioral techniques to try to get them to charge at selected hours. These are some examples of how we do that. We'll, for example, actually take the data off the cars, clean it and put it in a graph form, of their own load shape, like shown on the right, and even give them a score for how well they're doing at charging at off-peak hours. And so this is an approach, again, where we just use the data and you have the customer set their own schedule, manage their own charging. But the other approach is using the data for, active load control. That could be traditional demand response, or that could also be schedule setting, where the customer plugs in their car and then they leave it to the utility through, companies such as ours to optimize and manage that charging for selected hours. And that could be to save money. That could be if there's periods of, stress on the grid, say during an event, or it could be because we get a signal, say that there's excess renewables on the grid. Thanks.
Thanks very much, Scott, and thanks for pointing out the importance of customer education. That actually will come in later panels when we do talk about privacy. Customers may be more likely to opt into programs if they see the gain and the benefit they're getting, the electricity that's saving, the monetary value they're achieving, and they might also themselves detect issues that can help, save energy as well. So that's a really great point. Thank you. And I guess we'd like to turn now to Mario to hear about additional benefits from the data.
Right. Yeah. No, I'm glad that both Anthony and Scott went first, so they could talk about some of these specific items that they have to look at. What we deal with is a lot of the same things. We try to improve, demand response. We try to improve the load control. We try to improve the utility capacity for both residential and commercial. There's a couple of things though that we've been directly working with in terms of health and particularly asthma. There are many sectors of particularly large cities and cities in valleys where traffic smog is a major health hazard. And asthma cases, as well as other respiratory illnesses, do rise in the face of transportation exhaust. Particularly in communities that are highly impacted by this, they tend to have fewer electric vehicles. And incentivizing electric vehicle adoption in some communities is incredibly challenging. EVs are still a fairly expensive vehicle, and used EVs, while they are picking up in the market, they are still relatively expensive, and their battery degradations tend to be somewhat high. So their range is limited. One thing that does benefit these regions, though, is, again, large-scale vehicle electrification. The problem with large-scale electrification, of course, and this is why we need the data, is if you're dealing with a freight electrification at 1 megawatt per truck, that's 1,000 houses that is suddenly put on the grid. And if you're charging 10 of these because you are Amazon at a warehouse or you are a Walmart distribution center, then it gets incredibly expensive for the grid. It is very hard. And as we mentioned, putting in a substation or putting in additional infrastructure is, again, an expensive but almost necessary component of this if we don't handle the charging sessions right. Luckily, with these large-scale vehicles, particularly buses, we can get very granular data on their position, the exact state of charge as they're driving. We can understand when different passengers are coming on and off. We can get estimates of the weight of these vehicles, and we can predict out to a fairly high extent what the pricing signals are from the grid, what the demand signals are. And when we have utility partners, they can signal to us like, hey, we need 10 megawatts, slow down the charge, right? And we do have capabilities to do charge curtailment on a lot of these endpoints where the EVSEs are located, and we could curtail the charges down into the low kilowatts. so that we don't burden the grid when train is leaving a station and that power draw is pretty high. When we know that there's a large electric event that needs to happen, we just need to reduce charge for an hour because of peak demand. These are things that we need to think about when we want to put in electrified autonomy for freight or electrified. Sorry, I say autonomy because we also think a lot about the autonomy side. But when we have these electrified transportation systems, when we want these health impacts to come down and we want these systems to be adopted, as Anthony and Scott both said, we have to think about how this impacts everybody. And that includes the utilities, that includes the end user. Is it convenient to charge? If it's too expensive to build a charging infrastructure, it's too expensive to think about how to charge, then it won't be adopted. And again, those health impacts will just continue to mount as more and more freight systems are being purchased and implemented in cities. So we think very hard about who's benefiting from these systems. And for fleet autonomy, for freight autonomy, mid and heavy vehicles, they don't always charge at the same times that residential charges. Residential charging patterns generally fall between about 4 o'clock, as was mentioned, to about 8 or 9 o'clock at night in charge patterns in your homes. But that's not the case for fleet and heavy duty vehicles. They also need to charge everywhere across the United States. And in other countries we deal with, they have to charge in places and times that, again, can be considered as peak times for most of these generations. Understanding what the right way to curtail, or to balance these charging events requires this data. We absolutely have to have this data. We cannot make impacts without understanding how these vehicles perform, how their batteries are really doing, what their thermal signatures might be, and how the actual infrastructure is handling the strain of these large charge events. They get really hot, these coils, both wireless charging coils and standard plug-in charge coils. They can get very degraded depending on the speed at which you're charging. These are all things that we think about when we get the data. Without it, we can't make the models, we can't build our AI systems, and we can't do the balancing that we need to do for large-scale adoption.
Thanks very much, Mario, and especially for pointing out, the health impacts that are really important and the disproportional effect of very large vehicles in terms of pollutants and electricity use. So Mario's mentioned, the need to sometimes curtail charging. Anthony and Scott both mentioned a number of different types of managed charging. And one of the questions that arises is, how well are all these policies working? And data can be used to measure the effectiveness of these policies, as well as effectiveness of new components and systems in the grid. So we'd like you to talk about the effectiveness, and it can be really challenging because, for example, you can measure the effectiveness on the current users of EVs, but they can be very different from the other users. You might be missing underrepresented or disadvantaged groups. If you just look at current users, you might be missing certain weather events, very extreme adverse weather that really greatly affects the grid as well, if you're only looking at pilots or initial users or initial regions. So we would turn to you now and ask, how do you currently use, or how do you foresee your organization using data to measure the effectiveness of these policies as well as new systems? And we'll start with Mario.
Yeah, and as we get to the policy, this is again where things get kind of interesting. Not everyone likes to give up their data. This is IEEE digital privacy. We know this. We don't want to take people's data. When it comes to buses, it's usually easier. These are usually managed by municipalities or by states, and getting the data from them is fairly transparent. We can get a lot of information, and we can get it at a fairly good speed with fairly precise GPS markers, as well as pretty much anything off the can. That's really nice. Usually, though, for individual users, when we ask users to give us information, there are some things missing. One example very recently, as we were putting a pilot in place for a city, is people have to opt into a scheduled charging. So we say, like, if there's a peak demand, we might lower your charge. Unfortunately, there was no way immediately for the user to say, hey, I really need a charge. Like, I need to leave in 1 hour. I think Scott mentioned this earlier too, but we don't know exactly how long people will charge unless they volunteer that information, and we don't always know. So if you plug in during a peak time and we're anticipating you're there for 3 hours, but you're only there for an hour, your car will not be very much charged at all. So there are pieces of information that right now we're just missing that prevent us from doing a very successful job all the time in managing charging. But we have had greater success when it comes to things like trains. If the train is pulling out, that's only for a minute. About 70 seconds. That's all we need. We just need to curtail the charge for 70 seconds. And that makes a difference, because that demand response is a very simple one. So for a short time, it does not impact the charging too much. But we can take care of, from the charger side, some of the logic to make sure that the grid isn't overly burdened. So I know this isn't a really good answer. Sorry, Linda, I know it's a bad answer, but the amount of data we get, depending on the type of vehicle, whether it's a fleet, whether it's heavy duty, whether it's a bus, whether it's private small vehicles, really changes the way we have to think about how to balance a charge. If it's 1 or 2 vehicles at a public charger, we often can't worry about the long-term peak charge time, just precisely for the reason that we don't know how long you're there. On the other hand, if we have to deal with a parking lot full of level 2 chargers at an airport, and again, that's another example of a pilot project, right, where we have over 100 chargers at an airport. At that point, yes, we're anticipating you're there for a long time. We're going to moderate that charge signal somewhat well. It's the one-off situations that we have the hardest time with, and that requires more input from the user if we want to really take advantage of the intelligent communication with the charger.
Well, thanks very much, Mario. And you have raised some good points that maybe Anthony and Scott, when they talk about effectiveness, might be able to address as well. Of, you know, how many EVs you're getting data from. That gets us into questions of, you know, aggregation when we're measuring effectiveness, and also just, you know, which vehicles are being, data is being collected from and how that works. So now we'd like to turn to Anthony to talk about effectiveness, how they measure effectiveness from the data.
Effectiveness of the data. So I think Mario touched on some very important points, even as it might relate to effectiveness of related to using data, but also in terms of, you know, policies. You know, our policies are meant to be very kind of broad brushes in an attempt to capture a large benefit across the you know, our population. But the reality is, you know, our population is very segmented. You know, I talked to you earlier about residential customers and the segmenting that we had to do in commercial customers, and segmenting it's not just vehicles. Maria talked about trains and all these other electrification options. There are planes that are completely electric that are flying that also need to charge at airports in the future. So, you know, we have to think about this very holistically, and really it's going to require sort of a surgical tailored solution that has to be managed in real time. It's to really optimize the benefits and really keep rates low for customers. You know, if it's on the policy side, we think about FERC pushing through FERC 2222 to low, you know, lower levels of aggregated DERs, energy storage, and electricity to provide grid benefits. Will it work? You know, will there be enough uptake of DERs to provide the benefits? There's always a question about, you know, how do we pay customers? So, you know, we have mechanisms in place, but the challenge is, will they work? We have to test them. We have to validate them. We are looking at the feasibility of real-time rates. All 3 utilities in California, Southern California, PG&E, San Diego Gas and Electric, are required now to cut this pilot, which we've already started to evaluate if we push prices, real-time prices, devices, how can we better manage the grid in terms of demand flexibility by just using rates? So it's going to be a combination of solutions in terms of, you know, potentially real-time rates if that works, managed charging, behavioral load shifting, you know, and careful coordinate and scheduling between customers or prosumers to optimize the grid. You know, we have standard TOU rates. We're able to evaluate that TOU rates do work, but you know, the challenge with customers is we still want to provide the best level of service. And is that standard TOU rate the best level of service? And maybe they would rather charge before 9 a.m. instead of 9 a.m., but they're forced not to charge. Maybe they might give something up in order to be able to do that. Or maybe they don't really have to because, you know, that capacity on their section of the grid is not congested. And so we have to evaluate, you know, all these benefits of load control, load shifting, conduct pilots and studies to validate, you know, what's the optimal combination of all of these solutions. I don't think it's a single solution type problem. I think having, for us, telematics, vehicle telematics at some point is going to be ideal to better understand at a granular level, you know, how much we can count on customers to participate, and for them to be able to realize, you know, benefits not just in terms of EV charging, but also from an affordability perspective. Because again, as a grid partner or prosumer, they have the ability to effectively lower their rates. You know, we continue to, you know, it's just an ongoing effort of continuing to evaluate through a series of, you know, studies, pilots, demonstrations, deployments. What's the effective, you know, solution? We have 4,200 different circuits of about 800 substations. They're all very different, and so, you know, can we use a more circular approach to kind of best optimize, you know, potential solutions to the grid so the customers, you know, have the maximum, you know, affordability benefit, so they're happy when they want to plug in their electric vehicles. So you know, maybe I'll just stop right there and then we can move on to Scott.
Yeah, thanks very much, Anthony. And I'll turn to Scott. It was interesting that you also pointed out there's, you know, different vehicles that things need to be tuned into, and the advent of real-time pricing as well will greatly impact things. We'll hear what Scott has to say.
I agree. Yeah, thanks. Yeah, and just to, you know, I guess, you know, back up to the question again, it was on, you know, how the data, you know, is able to be used to demonstrate the effectiveness of policies and programs as well in that. And I'd say the biggest challenge I see is on the counterfactual. And, you know, I know that my panelists are talking about, you know, airplanes and trains and, you know, cars as well. I'm focused more like right now on existing programs, because I see a range of, you know, either rates or DR, you know, programs, you know, behavior programs. And, you know, what's the baseline? What's the counterfactual? What would the customer have done in absence of that? So some programs and pilots, I know, Anthony, you're running some, like they dive right in sometimes and they want to run a program. And, you know, I think it's really critical right now to, you know, either have a baseline period, have a split sample, have a control group, or do something to understand what typical charge patterns look like. And, you know, I'll give one example, which is there was an evaluation of a Northern California utilities DR program. And the evaluator came back and said the savings was 0.05 kW, the 0.05, not 0.5 even, or 5. And, you know, AC programs, DR programs, you know, on the residential side typically save about a kW. So it was a fraction of that. And I'm seeing other DR programs and load management programs, you know, come back. And it's because these customers, if they're already on a time of use, you know, rate, right, any rational customer is going to set their charging to a lower cost period, which often is off peak hours already. So we really have to differentiate, okay, what's the impact of the TOU rate? What's the impact on the DR event? And so the biggest challenge, again, I see is on the counterfactual and making sure that we try to use data to inform that.
Scott, thanks for that really excellent point. And that the forming of a baseline or the idea of a control group is really important. And this brings us to more general questions about data quality and the inferences and conclusions we're obtaining. It's really important that we do have control groups and that we know the error is in our data, as well as the uncertainty in our conclusions or forecasts, because these are being used to make important decisions. And it could be hard to find a baseline because it's moving once real-time pricing comes in and EV penetration increases, that baseline may itself be shifting. And so this can give us some real data quality issues, as can errors that are introduced from sensors, communication networks, human errors, cybersecurity attacks. So there's lots of sources of errors. There's also a lot of potential sources of statistical biases just because the early adopters aren't the same. Geography is different, and regulations and pricing and economic markets are different in different locations. So there's a whole bunch of potential data quality issues. And I guess we'd like to hear more about what data quality issues you're finding most challenging and how you're handling. And I guess we'll start with Scott.
Mm-hmm. Yeah, the data quality issues, I would say, to start off, when, we look at telematics data, we actually don't get KW and KWH. We just get, is the car charging? Yes, no. We can tell when and where it's charging. And so trying to convert that data into KW and KWH is challenging. It really varies, I'd say, also by OEM. So we have had to put a lot of time into our own algorithms to make sense of the data. We see things like the car goes to sleep and then it wakes up and it tries to reset the battery level. So it might look like maybe the car, say was charging at a certain time or, was not charging at a certain time because there's noise in the signals as we ping a car and download data. So, again, I think the biggest challenge is trying to look across OEMs, analyze that data, and then pull it all together into something that's usable for utilities.
Nice, that's great. Anthony, what are the biggest data quality challenges you're finding?
Yeah, sure. So contrary to Scott, so we do get our KW and KWH measurements. Unlike Scott, when he knows when cars are charging and stop charging, we have to infer that from the data. So if we need to know a little bit more about charging behavior, we have to write algorithms to do the disaggregation to understand when customers are really charging and not charging. Now, in terms of data quality issues, so most of the work that we've really been doing has been sort of on an aggregate level, where we're looking at different residential segments. So, we have our control group for residential segment, customers that don't have EVs, and then we have all the other segments in residential categories, whether they have PV or energy storage, which is very few, but also whether customers are not on time of use rates, on time of use rates, specially designed for electric vehicles or other time of use rates. And then I mentioned earlier with the commercial vehicles, we have a number of other segments. And so because we look at these segments sort of at an aggregate level, the data quality issues, there are some sort of noise. I think when we start to integrate DERMS and the ability to let vehicle telematics data, the accuracy of the telematics data is going to be a lot more important. And there's always challenges with sensors not working and RTUs or whatever, and having to impute the data, infer from it, and evaluate what are the impacts that kind of result from it. But in terms of overall challenges with the data, I wouldn't say they're mostly been data quality challenge. I would say mostly, like I talked about earlier, the fact that most of our residential EV customers have a single meter that combines residential EV charging loads and all the other building loads, air conditioning, washer, dryer, lighting. And so in order for us to really study electric vehicle behavior, we have to find a way to disaggregate the load. And because we were studying, EV charging behavior for a while, we were able to develop an internal method to do that. where at an aggregate level, we're able to use it to inform standards and help us do predictive analytics like forecasting to help with transformers and aggregate system forecasting load. The other challenge that we had was initially with the rebate programs, we could only identify 40% of our electric vehicle customers on the grid. And so in order to do representative studies, we really need to know where more customers are located on the grid. And so we had to develop a EV identification methodology, which is good enough accuracy for the aggregate level of work that we did in order to identify the other EVs, to better inform standards, to also help identify optimal EV charger locations for residential customers. Now that we know where more of the EV customers are, we know also have the ability to better target EV customers with energy management programs through customer service. The other I guess you could say processing that we're really interested in doing is just with studies, but also when we think about integrating vehicles real time, ADMS and DERMS, and leveraging the ability to optimally control voltage and thermal violations and keep affordability costs down. I think there's still more work to be done and more data that needs to be gathered as it relates to understand price elasticity with incentives in terms of technologies like managed charging to further understand demand flexibility, and again that's would require a tailored approach versus kind of a broad brush approach to understand where are we likely to truly see the benefits of customers in terms of being able to support capacity needs and also be able to leverage these new resources to provide short-term emergency needs, for example, with climate issues such as extreme heat. Like earlier this year, we had 5 days of flex alerts, which were basically warning signs that maybe we had to disconnect customers. So, these are some of the future areas of how we need to gather and process the data to learn from, to evaluate what's possible and what kind of solutions are we likely to be successful with some level of confidence.
Well, thanks, Anthony, and thanks for bringing up the point that in certain circumstances, you're really looking at the aggregate and you're looking to the future to figure out how to best process data. So this brings up another question, which may be of interest to people concerned with privacy, as well as to the concern about monetary expense and energy expense. It does cost money and power to move energy through the communication networks, and they're working on making this more efficient, but it still is a factor to consider. And in future panels, we'll discuss the privacy aspect, but it may be advantageous in certain circumstances to leave more of the data at the edge, do more edge computing, and sort of collect more of the aggregate data at the destination. So I'd like to turn to Mario and then Scott to ask them, is all the data collected at the source sent to the destination? Is anything currently processed at the edge or on the way? Or in the future, do you foresee more edge processing? And we'll start with Mario and then go to Scott.
Yeah, that's a good question. When it comes to the edge compute, right? As much as we can, we prefer to limit the communication. We don't want, especially if it's a moving platform. If it's a mobile platform like a vehicle, right? Apologies, I have to try not to talk about autonomy. If it's a moving platform, we really would prefer as much of the edge processing to happen as possible. If it's connected to a reliable network and we can get data off of it at a fairly fast uplink, so if we know we have photovoltaic on a charger system and we know we've got the EVSE actually connected, then we'll take that at whatever speed we get that naturally. We can handle things on the server side. So sometimes when we aggregate and say, all right, just give us the last minute of information as a single packet, or less, right? Depending on the speed and ability of the devices that we have on hand, as well as what sensors we're getting. Sometimes sensors are spamming things at 300 hertz, at that speed, we just don't have the network ability. Or on the server side, if we're dealing with over 600 connections, we just can't accept 600 connections at 300 hertz. So at times we'll just let the edge device say, are you healthy? Are you communicating right? And give us a little bit of aggregated information. I'll maybe Scott will elucidate a little bit more on this.
Yeah, I was going to say, I mean, in terms of telematics, as of now, we have to ping a car and we have to download data. And I showed earlier the fields that we get. I think the real, richness is in the post processing of that information and what you can do with it. I mean, at this point, we can pull thousands of cars, at a time and get that information. What we would like to see going forward instead, we are actively talking to OEMs about this, is getting data when there's a change of state. So leave the car alone, let it sit. And then when it, it starts driving, then it sends out data when it's done driving, when it plugs in, when it's done, charging, because that has the ability, to minimize just the amount of data we could, that we have to pull down, as well as any risk in terms of, battery drain by having to ping the car.
Great. Yeah, thanks, Scott. That's sort of opportunistically sending out the data, sounds like a good plan. I guess we're nearing the end of the hour, so I'd like to turn to audience questions and comments. There was a comment from Brian McMillan that real-time pricing was an abject failure in Ontario in the early 2000s. The customers revolted when prices spiked. So real-time pricing is already starting to move forward in California. We do expect it here. Does anyone want to talk about how there might be better experiences or advantages with real-time pricing and how data can help with that in the future? Please chime in if anyone wants to speak about that.
Yeah, there's one example I saw in the Midwest. It's, it's called real time, but it's really day ahead pricing. And that seems to have worked well, especially with EVs, because the customer knows in advance. And again, that's an advantage of being in a program, is because if they have signed up for, say managed charging, it allows them to know that, okay, these are the hours they don't want to charge tomorrow, so they can pre-charge if they want. And then they don't have to worry that their EV will be charging at those hours, because again, if we're managing the car, we can set the schedule, or we can pause charging if they see if they are charging, say during a, high priced period, for example.
Thanks. Does anyone have anything else to add?
Yeah, well, what I might add is I think, real-time pricing today versus, several years ago is quite different. So today we have a lot, more sophisticated, building energy management systems that integrates EV, PV, and energy storage, that can build in contingencies to manage, downside risks for customers. So the objective of these pilots is to really learn, how things change. What more can we do with technologies, and are there any benefits? So I would say, stay tuned over the next couple of years, and we'll learn more.
And I'd like to just also add to what Anthony said as well. With the real-time pricing, there are some systems that will come in place that are automated, and customers can type in their preferences. For example, they only want their heat within this range, and they're willing to, give up use of this or that appliance. And similarly with the EVs, they can say, what they're willing to do when they want their car charged by, but within those parameters, then they're willing to abide by real-time pricing, and it can happen in an automated way. So I think the real-time pricing does still hold some potential promise for the future, but a lot does need to be worked out. So we're at the top of the hour, and does someone want to add anything? Okay, well, I'd like to thank all the IEEE staff and volunteers who helped organize this panel. I'd also like to particularly thank our three panelists for sharing all their expertise and experience. Finally, I'd like to thank the audience for tuning in and for their great questions. And we look forward to continuing this discussion and focusing on the privacy aspects in the future sequel panels to this event. From this event, we've learned a lot about what data is collected and why it's really important, and how it can really help with the clean energy transition, other benefits to the public with like health benefits, and reliability of the grid. Thank you very much. We look forward to joining you in the future.
Thank you.
Thank you.